Yep.
Okay, welcome to the second session of this day. We are going to have talks, and you will be able to make your questions through the Q&A chat, and the questions will be answered either online or written in the Q&A. So that's it. The first talk is the Sahid Hampu Yaril. Sorry if I mispronounced. Evaluation of medium range near surface atmospheric forecast over Antarctic and surrounding Southern Ocean. So Sahid, you can.
Yeah. Thank you, Adriana. Can you hear me?
Yeah. Crystal clear.
Okay. So I'll share my screen.
Yes, please.
Hope you can see my screen.
Yes. It's not in presentation mode yet. Yes, now.
Okay.
Great.
Welcome to all.
You have 10 minutes.
First, yeah, thank you very much.
Okay.
Yeah, welcome all of you. Thank you very much for inviting me for this conference. Myself, Shahid. I'll be presenting a few of my results on the topic mentioned over here. So the evaluation of near surface Antarctic atmospheric forecast from the NCM, which is a version of UKMetofis atmospheric model, and of course it is a part is this. The initial conditions are prepared and run in National Center for Medium Range Weather Forecasting, NCMRWF. So we call it as NCUM. The context of this presentation is like in the polar regions, the main focus is on the forcing of sea ice by using atmospheric forecast from the NCM. So, of course, in the coupled modeling system, the biases in the ocean and atmospheric, basically the sea ice parameters. So, sea ice parameters are depends on the forcing. Generally, this forcing is we have taken this forcing from the atmospheric component of the UKMetofis model, unified model, and it is important to evaluate the forecast of NCM in the context of a sea ice forecast. We generally used to give sea ice forecast for our sister institution like National Center for Polar Ocean Research, NCPR, which is also the hosting institution for this conference. And we'll be looking at some of the parameters on the near surface in the context of the sea ice forecast that we used to provide for NCPR for their operational purpose, in fact. So at the NCMRWF, there are different sets of modeling systems. We have at NCMRWF 1.5 regional model, which is 48 for forecast, and then 4-kilometer regional for 72-hour forecast, and then of course the one we're talking about 12-kilometer global model up to 10 days forecast, which is the atmospheric model. And also we have a coupled modeling system which provides a forecast up to 15 days. Of course, we know that the variabilities in the Antarctic and Arctic, it's completely opposite. We have the maximum sea ice in the Arctic in the March and the minimum in the September, whereas the variability, the seasonal variability is much higher in the Antarctic, where we have almost 18 million square kilometer of ice in sea ice, and then it shrinks to a minimum of around 2.5 or around 2 million square kilometer in February, March. So large variability in the sea ice. Of course, the onset of generally we used to provide the sea ice forecast for the operational purpose of NCPR, and we know that there is huge variation within days of onset. Like sea ice can form from nothing to within few months it can build up to a maximum of start 10 to 18 million square kilometer within 3 months. And the onset of this, and definitely we found that the forecasting in sea ice, basically the onset of sea ice, melting onset of sea ice, sorry, the freezing onset of sea ice is very important during the operational purpose in polar regions. This actually in this section of my 3 regions, and we can see that then if you zoom in over here, like my 3 region, of course, the sea ice, but basically, for operational purpose, it's very important to have the forecast in sea ice. This is sea ice thickness. Previously, this was actually sea ice concentration. This is sea ice thickness. Yes, has larger spatial and temporal variability within a shorter time scale. So we're just like assessing the skill of the model, which is in forecasting the sea ice. This is generally a couple model. These results have been presented as couple model. Of course, we have seen that we have the ocean component, which is forced by the NCM model. Basically, the sea ice forecast for 10 days. And if you found that well ahead of 15 days, the model is able to capture the variability. Basically, you can say the onset of freezing and ahead of 15 days. So coming to then, generally with these forecasts have been basically the sea ice forecast from the ocean side, like you have a standard ocean model with sea ice with no coupling to the atmosphere, but the forcing is given by the medium range forecast from the National Center for Unified Model. And as part of this work, we understand that it's very important to evaluate the forcing component, like basically the near surface Antarctic variables, which is giving us a forcing for the ocean model for the 10 days forecast. So this is just a comparison between the couple model, near surface variables, and the atmospheric near surface atmospheric variable from the standalone atmospheric model and the couple model. In this case, I don't want you to have a comparison between the couple model and the standard model, because I want you to have a comparison between a coarser model in the couple, which is N21216 model. It's a very coastal grid in the atmosphere, 65 kilometer around the resolution, but this is 12 kilometer model in the atmosphere. It's a NCUM. This is a couple model. This is NCUM. It's a standalone atmospheric model. So from 10 day 5 onwards, the biases are basically in the winds. You can see a lot of false alarms in the near surface. From day 5 to day 7 to day 9, up to, I haven't shown here 1 to 5 days because, of course, the biases are not that prominent, because the forecast is really useful up to 10 days. And after that, the atmospheric, you can see the atmospheric wind over here, which is, you can see a lot of false alarm, which is almost similar in the couple model as well. It's just a general circulation point of view. If you don't look into the minute scale of the minuscule scale in minuscule scale, like this is basically this is the MSL. Sorry, actually, this okay. Mean sea level pressure. Of course, there is the biases are more widely spread in the couple model, whereas you can see the biases are almost the same otherwise in the atmospheric 12 kilometer model as well. But that's not the case when we move. Okay, moving to the 2 meter air temperature, you can see large cold bias in the basically the sea ice regions. Of course, it would be having an influence on the sea ice forecast, and in the couple model system, that's something that we have analyzed before, and still we are doing some other work related to that. In the couple modeling system, how does the biases in the atmosphere affects the sea ice forecast? So you can see that this from day 5 to day 9, the warm bias in the NCM standalone model is increasing, whereas you can see this cold bias in the coupled model system. This is actually, sorry, I forgot to mention that this is in the July, August, September, which is time actually we have the maximum sea ice in the Antarctic, and this is a time where, yeah, this is another year, August and September. This is 2017, and this is 2018, in fact. Similar is the case in the, yeah, I'm almost finished. You can see this, basically this is relative humidity. In terms of relative humidity, the bias is almost the same thing you can see, just like we see over in the other parameter as well, that the bias is more widespread in the sea ice region, especially during the peak, you can say peak winter season in the Antarctic. So very short summary. Of course, the model is forecast is much better up to 5 days. In fact, even though I haven't shown here some of the plots from it, but otherwise the biases are starting to grow much higher from 5 days to 10 days, and the skill of the model is better in the initial days, and after that, the biases are increasing. So an extended work of this will be done soon, like to have more inquiries into the reason for the bias and then fluxes into the system. Thank you for listening.
Thank you. If there's questions for Sahil, you can write it down in the Q&A. Okay, so meanwhile, Dr. David Bromwich is going to present 2 talks in a row, an overview of the year of polar prediction South Hemisphere 2022 winter spatial observing period, and Antarctica data impact experiments with polar WRF during the envisaged summer spatial observing period.
Okay.
You can stop sharing your screen. So,
yep. Okay. There we go. Thank you, Adriana. Okay, so I am going to talk about the YOP-SH winter spatial observing period that's happening right now. In the background is a picture of a radiosonde released just recently from Rothera Station on the west side of the peninsula. Okay, so to outline, we're going to have a brief introduction. We're going to talk very, very briefly here about the summer spatial observing period. I'll deal with that in the second talk. The main part of this talk is the winter spatial observing period. This is on the right of radiosonde release during this SOP from McMurdo. Okay, so this is under the umbrella of the World Meteorological Organization Polar Prediction Project, or PPP, 10-year project that's ending this year. And the broad goal is to promote research toward improved environmental prediction for the polar regions and beyond. There was the year of polar prediction, 2017 to 2019. In the Southern Hemisphere, we started later and we're going 2 years beyond. A similar goal, we had a summer spatial observing period in the 18-19 austral summer. Okay, so just to expand a little bit on what the previous speaker talked about, this is some results from the European Centre High Resolution global deterministic forecast system. This is the anomaly correlation coefficient of the 500 HPA geopotential height, 1200 12-month running mean. The blue is 3 days, the pink is 5 days, the green is 7 days, and the yellow is 10 days. So as you go out in time, the forecast accuracy decreases. So for the top in the blue, the dark blue line is for the skill. So getting towards 100% is where you want to be, is for the Arctic poleward of 60 north. And the thin blue line is for the Antarctic poleward of 60 degrees south. So the Antarctic is lagging behind the Arctic in forecast skill. However, both regions, the skill is steadily improving, particularly since the late 1990s. And a metric is 60% is useful. So even out at 7 days, the forecasts are, quote, useful. I'll skip over this because I'm going to talk in the next talk about this. Okay, to really talk in detail about the winter spatial observing period that's been going on since the middle of April to the end of August, we're going to use these targeted observing periods, limited people, limited personnel, and we're getting additional radio sound ascents from all these stations shown by the red dots on the right. And you can see there's a circumpolar effort by the international community contributing to this. 2 broad regions, I'll talk about that in a moment. So this is a really major addition. The 2 regions we're looking at are what is called the Ross Sea to East Antarctica, and another focus area is in the Antarctic Peninsula. We're looking in particular at weather and climate phenomena over the high southern latitudes, so characterize them in more detail, such things as major coastal cyclones, atmospheric rivers, and clouds, pervasive cloud problem. The other big area of the YOPSH is to look at the impact of the additional radiosondes on the weather forecasts, and can we do a better job of predicting the extremes. There are, in addition to the radiosondes, there are these enhanced measurements, particularly in the Antarctic Peninsula. This is a table for Escudero on King George Island, Rothera on the west side of the peninsula, and Marambio just around the corner on the east side. And there's a lot of radiation measurements from the ground, which give us indirect information about the clouds. There's some active sensors like this micropulse LiDAR, which gives us information about the cloud height and thermodynamic phase. And I'll talk about some additional instruments in a minute. Also, there's quite an effort going on at Davis along the coast of East Antarctica. 2 instruments I'll highlight is a VHF clear air wind profiling radar, which basically gives you horizontal and vertical winds throughout the depth of the troposphere to the lower stratosphere every 6 minutes. And this micro rain radar, which is at a number of places, including in the peninsula, which give vertical profiles of precipitation reflectivity, vertical motion, and precipitation rate. I think a particularly interesting sensor is these Anosphere sondes. They're attached to regular radiosondes, as the picture in the lower left show. It's the bottom fixture. They're basically a vibrating wire on which the deposition of water species changes the frequency. So you release those and they give you direct measurements of the cloud liquid water and cloud ice. They're taking place at 3 places in the peninsula, Terra Nova Bay and Dome Concordia in the high interior of Antarctica, not at Davis, unfortunately. Okay, so to further the previous talk, there is this effort going on called the Sea Ice Prediction Network South that are looking at, or have been looking at, the forecasts of the sea ice minimum around Antarctica. And this has been going on for a bunch of years. The black dashed, small dash and large dashed lines are the for the 21-22 austral summer. And there's all these different contributions that you can see by the acronyms. But basically, the coupled models do start out to be significantly higher in the circumpolar Antarctic sea ice extent, and then eventually catch up. So they're too big to begin with, and then melt too rapidly. As part of YOPSH in the winter, they'll be looking at the growth period from May to August in 2022. A particularly nice tool that was generated by our colleagues from the Scripps Center for Western Weather and Water Extremes is this atmospheric river diagnostic based on the GFS forecasts. So there's this scale that is in the left panel, and this tool shows, amongst other things, the maximum forecast atmospheric river scale for all these points around Antarctica. And then on the right-hand side, there's an animation. I just show you one panel of that, of the integrated vapor transport. Okay, so right now, as I said, the SOP is going on. Within this, there are these targeted observing periods, the TOPs. We're at the present time under number 6 for East Antarctica. It'll be winding up in about a day from now. They're sending us very nicely from the different stations, pictures of the releases from all these different places. To give you an idea of what's been achieved so far, I've done the counts for tops 1 and 2, Antarctica wide, and we're roughly more than doubling the routine observing program per day. Okay, so to summarize this, the summer spatial observing period, I'll talk more about this in a minute, was a big success. It does emphasize the forecast over Antarctica. Right now for the winter, there's great enthusiasm by many nations for this winter SOP, and based on the results from the summer that I'll show you in a minute, we're making a big effort to launch the radiosonde balloons north of 60 so we can get better forecasts of the incoming cyclones, atmospheric rivers, and so on, to better understand and predict the extreme events impacting coastal Antarctica. So hopefully I'm fairly close to 10 minutes.
Yeah, just on time. There's a question for you. Sir, summer expeditions could be challenging on their own. How are winter expeditions in Antarctica comparatively more challenging?
Yes, well, the weather doesn't cooperate very much in the wintertime. There's lots and lots of storms. There's more aircraft operations in the summer for medical reasons, and also expansion of the field season on a limited basis into the winter. We want to be able to improve the forecast so we do better, particularly for the big events in the winter. And that's our goal. Hopefully we'll be able to achieve it. But yes, it is challenging in the wintertime, much more challenging.
Great. So if there's no more questions, you can share your other presentation.
Okay. Okay. Everybody can see that, hopefully.
Yeah.
All right. So the title of this thing is Antarctic Data Impact Experiments with Polar Warp during the YOP-SH Summer Spatial Observing Period. Okay. So just a little bit of an outline, once again, of this, after the introduction, some outline of the achievements in more detail, results from the summer, which I'll go over in detail, and wrap up. And this is a nice picture of the first balloon launch from Dumont Deville Station on the 16th of November, 2018. All right, I pretty much have said this before. So the YOP-SH component of this focuses on observation and prediction in the high southern latitudes. I'm going to be talking in detail now about the summer spatial observing period, which was middle of November to the middle of February in 1819. And primarily we had additional radiosondes. We also had some additional drifting buoys, automatic weather stations, and ship observations. I've already talked in detail about this, so I'll go beyond that. Okay, so as far as the summer spatial observing period, on the right here is a picture of all the different stations that participated, and the numbers attached to these locations are the additional radiosondes that were launched during the summer spatial observing period. So during the summer, there's a lot more people around, so there's a lot more personnel available to release these balloons. So in contrast to the winter, most of these stations released these additional radiosondes throughout the 3-month spatial observing period. So there were about 2,300 additional radiosondes sent. That's over and above the routine launches. And there was a lot of different stations. Once again, it's circum-Antarctic, but not too much. The farthest north that participated was Macquarie Island. And you can see the ships around, mostly small numbers of soundings, except for the Polarstern, the German icebreaker. It was about 120 additional soundings. So the Polarstern and Neumeier went to 4 soundings a day during their enhanced observations. Okay, and we've done a lot of planning for this. We've got another workshop coming up in Madison, Wisconsin, towards the end, in Saturday of this week, in fact. Okay, so talk about the results. We have the radiosondes. What kind of impact do they have? So we're going to do these data denial experiments. And to give a broad summary, I'm going to show you better forecast results both at the surface and upper levels. I'm going to show you one example where this particular low pressure center was better captured along the coast of West Antarctica. Talk a little bit about atmospheric rivers as another case study. Okay, so talking about these data denial experiments, this is a joint project between our group in Columbus and the National Center for Atmospheric Research. We're conducting model forecasting experiments by varying the number of observations. So what we do is I'll come back to it in a minute, but basically we run the forecasts with and without these additional soundings in the initial conditions. And we're asking the question, do the additional observations improve the forecast significantly? There's a lot of satellite data out over the Southern Ocean, so it's not a foregone conclusion that we'll have a big impact. The framework we're using is the Antarctic Mesoscale prediction system, which is shown on the right. We use the 2 domains, the 24-kilometer domain which is not square, but rectangular. And it is targeted particularly at the aircraft flights out of New Zealand to Antarctica, to McMurdo. And in addition, we're using the higher resolution grid, 8 kilometers over Antarctica. We looked at 3 summer spatial observing periods, and I'm going to show you the results from the 1st to the 17th of January in 2019. Some terminology. I'm going to use the term no SOP, which means it assimilates everything in the initial conditions. So the soundings, the surface observations, the satellite radiances. SOP is the same thing, but the addition of the extra radiosondes that I just mentioned. Okay, so here's the heart of the talk. So this is looking at the forecasts in the top row of the temperature, in the middle of wind speed, and in the bottom for relative humidity. And so it's arranged in pressure from 1,000 to 20 HPA, so basically the surface to well into the stratosphere, for forecast hours 0 to 72, so out to 3 days. All right, and the left-hand column is south of 60 degrees south and north of 60 degrees south to the right. So the reds, we're comparing the forecasts of to the Era 5 global reanalysis, which we are taking as truth. It's approximate truth, but it's the best that we have. And we're looking at the mean absolute error, and the no SOP minus the SOP. So if the SOP mean absolute error is smaller than no SOP, the forecasts are better. It's plotted in red here. And you can see that south of 60 degrees, so 60 degrees runs roughly through the northern tip of the peninsula, has a lot of ocean there close to Antarctica. The forecast temperatures are substantially improved in the lower to mid troposphere, and they go throughout the 72 hours. There's a peak around the high troposphere and up at the model top. For the wind speed south of 60, there's a different configuration. This is reflecting the horizontal temperature gradients in the atmosphere, and it's at the jet stream level, and it tends to be maximized later in the forecast. Same thing for the relative humidity. It's maximized later in the forecast. If you go north of 60, where there was very few additional observations, the impact of the additional observations did diffuse northward. There is a weak reflection in the temperature, wind speed, and relative humidity later in the forecast. Okay, so there is a definite positive impact of having all these additional radiosonde observations, even in the context of the vast amount of satellite information that goes into the models. Okay, so let me show you one example. This was a low pressure system. The colors, probably focus on those, is the mean sea level pressure. So there's a fairly intense low pressure system around 960 HPA around the Pine Island Bay region. And the SOP is on the left, the no SOP where we don't have the additional radiosonde observations on the right. You can't see much difference. On the bottom row is the difference of the forecast fields compared to the Era 5 global reanalyses. And the magnitude of the differences are smaller when we have the additional radiosondes, as you would hope. They're qualitatively the same. So we've just decreased the magnitude of the forecast errors in the 24-hour forecast. Okay, there's an automatic weather station that was service just before this event, so it was fully operational. It's called Austin. It's shown by the red triangle. On the right-hand side, we have the time series of the observations in black. So for surface pressure, temperature, and wind speed. And in green, over this 5-day forecast, we have the ERA 5 global reanalysis. It assimilates these observations, so it should be accurately reflecting them. And then the two forecasts, the SOP in the red and the no SOP in the blue. And they follow the mean sea level pressure, the surface pressure trace fairly well, although the errors start to get significant by forecast day 3. And certainly there's the SOP is significantly improved in relation to the no SOP. The temperature regime, actually the two forecasts do better than the global reanalyses and capture the diurnal cycle very well in forecast days 4 and 5. So that's a function of the forecast clouds. The wind speed forecast actually was exceptionally good at this one location for 4 days into the future, no matter whether you use the global reanalyses in retrospect or the two forecasts in real time. Okay, so there was this atmospheric river case. I'll just go over this quickly. I'm sure I'm running short on time here. This was during the summer SOP, and there were observations from Punta Arenas on the southern tip of South America and on King George Island. And this atmospheric river is shown by the integrated water vapor transport with the dark blue of big values. And so from the subtropics across Punta Arenas spiraling into King George Island. So there were observations of like the cloud liquid water, the cloud ice, the radiation, and so on, precipitation. So how are the models doing forecasting these events? They need improvement, a lot of improvement in this area, actually. There was this nice study by Vicky Heinrich from the University of Tasmania, where she did this survey looking at how useful are the different weather information items. So she interviewed about 70 people that had gone to the ice and also the mid-latitude islands and asked questions like which were most useful or not useful at all. So from her survey, it's arranged, so green is most useful, and it's the plot is from the most useful to the least useful, and the most useful information was wind information, the weather information and advice from trained weather professionals, and then forecasts. So that's what we need to emphasize in our forecast for users. Okay, to summarize then, I think you might agree that the summer spatial observing period was a big success. The results show that the forecasts over Antarctica have been significantly improved with the additional radiation ascents, especially from the Antarctic interior. Okay, that's it. Thank you for listening.
Thank you, David. Okay, so you can ask your question in the Q&A chat, but since we are kind of little delay, we can let Dr. Harrison to present while you can ask the questions in the Q&A, and there will be some time at the end to discuss the 4 preceding papers. So Dr. Harrison, would you please share your screen?
Okay.
Thank you.
Let me try sharing now.
You will have 10 minutes.
Okay. Has that showed up in full screen?
Yes, yes, you can
That's
start.
great. Okay. Well, so I mean, we just heard how useful wind speed and direction information is, so that leads on nicely. This is some of the work that I've been doing over the last year or so, during my postdoc at the British Antarctic Survey, also in collaboration with the National Oceanography Centre. And so broadly, the project is about the Antarctic coastal easterlies, or the so-called polar easterlies. And this first part is about their representation in reanalysis data sets. So to give you a picture of what they look like, this is the long-term mean ERA 5 10-meter kind of wind field for the period 2010 to 2017, which we analyze. And you can see these kind of terrain following surface winds across the Antarctic continent, and then developing a more easterly component as you approach the coast. And then also you've got this red contour here, which is the contour of the 4 meters per second 12-hourly standard deviation. So that's kind of where the variability in the short-term wind speed is very high. So you've got this band of strong winds extending to this band of quite variable winds across the coastal margins. And if you take a cross-section through one of the East Antarctic stations, Mawson, you've got the orography plotted here, and then this is the U wind. So the blues indicate easterly or into the page, and I've just plotted the kind of long-term mean radius on data as well on the top there. But you can see these terrain following easterlies and then extending out across the ocean as well. We also have this kind of weaker, fairly deep easterly layer weakening as you get out across the ocean. So why do we care about the coastal easterlies? Well, in part, it's because of the role that they play in driving the Antarctic coastal current, which in turn is important for transfers of ocean heat towards ice shelves. But of course, they also play an important role in sea ice formation, as we've seen, and sea ice distribution, and eventually sea ice loss during the melt season as well. So we ask two main questions based on the fact that reanalysis data sets play such an important role in our understanding of these coastal easterlies. So firstly, how well do the reanalyses represent the spatial patterns and the short-term variability of the surface winds within the coastal easterly sector? And then secondly, to what extent is that representation sensitive to variations in the driving flow regime? I'll explain that more in a minute. So the first tool that we have to answer this question is the scatterometer data set from the ASCAT instrument aboard the METOP satellites. And so we look at the period 2010 to 2017. And we use the remote sensing systems version of the scatterometer data set. So that's the 10-meter neutral winds. And then we compare with the reanalysis 10-meter neutral winds as well. And so we look at ERA 5, MERA 2, and JRA 55. And yeah, just before I interpret these plots, the important point to make is that these ocean scatterometer winds are open ocean winds. So they're only available over regions where there's no sea ice. So that explains some of the gaps that we have in these plots, and also explains the fact that this is mostly a summer picture, so really constrained to the January to March period near the coast, which is the region that we're interested in. So this is the reanalysis minus ASCAT wind speed. So the blues indicate where the reanalysis wind speed is low compared to ASCAT. And you can see that for ERA 5 and MERA 2, there's a fairly similar picture. So this general negative bias with respect to ASCAT, but increasing somewhat as you approach the coastal margins, and in some regions exceeding 2 meters per second. Very much more of a mixed picture for JRA 55, but still this tendency towards greater bias as you approach the coast. And there's more missing data for JRA 55 because it's 6 hourly instead of hourly that we have for ERA 5 and MERA 2. To understand a little bit more about the representation of variability, we can look at the scatter plots, and these are only calculated for this coastal easterly domain, which we define here, so the region that's within that red contour. And you can see that overall the correlation coefficients are actually fairly high, perhaps not surprising given that the ASCAT data is assimilated into all three of those reanalyses for that period. But there's a bit of nuance to that as well if you look at the scatter plots. So with the reanalysis wind speed up the y-axis and the ASCAT along the x-axis, you can see that there is this tendency towards greater negative bias at higher wind speeds. So that's perhaps most apparent or most obvious in ERA 5, above around 20 meters per second, but it's also the case for the MERA 2 and even JRO 55, which doesn't have this kind of overall negative bias, but has more scatter around the 1-to-1 line and a generally slightly lower correlation coefficient. So the second part of the analysis is asking the question, to what extent is the representation of the low-level winds in the coastal region within these reanalyses sensitive to variations in the driving flow configuration or the local flow configuration? And for this, we're using station data from coastal stations. There's a bit too much detail to go into if I include all of them, so I'll just focus today on Mawson and Neumeier. And to flip back to the first slide, just so that you can see where that is, that's Neumeier here and Mawson that I pointed out earlier. So what I mean by the local flow configuration is kind of the local mean sea level pressure pattern. And to characterize those for each station, we use a self-organizing map algorithm applied to the ERA 5 mean sea level pressure fields. So you end up with these composites of mean sea level pressure for a number of different kind of representative patterns or states for that particular station, which in turn is important for the winds, in part because of the strength or the direction, but also in a way also for the processes that are driving those winds. And then below these maps of MSLP at Mawson, we have the scatter plots and wind profiles for each of these states. So instead of across the whole period, these scatter plots and wind profiles are presented individually for each of those kind of representative states. And this is just for ERA 5 in this slide. You have, again, the reanalysis up the y-axis and the observed along the x-axis. And then the profiles here, the solid lines, black for wind speed, green for V wind, blue for U wind, and red for temperature. Those are the observations, so the SON descents. And then the dashed is the reanalysis. And then shaded in the background is the correlation coefficient between the wind speed from the SON descent and from the reanalysis at that level. So there's quite a lot to unpack here, but what I wanted to draw your attention to today was just the difference between these kinds of states where there's quite a strong pressure gradient, there's quite a strong synoptically driven wind at that station on the one hand. So for those states, so including, for example, 1-1 here or 0-2, the range of wind speeds is quite well captured by the reanalysis. So it sort of follows the 1-to-1 line, although there's this, again, negative bias, at least in ERA 5 as against ASCAT. But by contrast, no worries. By contrast, these states which have more of a kind of low pressure gradient but still this strong terrestrial flow towards the coast, but cut off abruptly, so probably more katabatically driven flow, the variability, the range of wind speeds is much less well represented by the reanalyses. And does that apply to the other two? Well, broadly, yes. So there are a few nuances in interpreting the other two reanalyses that I won't have time to get into, but this overall kind of regime behavior and the performance is consistent between the reanalyses. And you can compare that with the picture at Neumeier, which is away from the coastal slope on the flatter extreme ice shelf. And that sort of behavior doesn't really apply here. So although there is variability captured by these different SOMs, the performance of the reanalysis with respect to the observations is not as sensitive to the SOM state. And these correlation coefficients for each of these three reanalyses are quite a bit higher through the wind profile. So I'll just leave you with some key takeaway messages. Firstly, the reanalyses do realistically represent the surface wind variability in the coastal sector, but the wind speed biases in all three of those reanalyses increase as you approach the coastal margins, and especially close to more complex orography. And there is this tendency towards more negative bias at high wind speeds. Overall, the correlation coefficients are highest in ERA 5, But again, all three of the reanalyses share this behavior of underestimating the range of surface wind speeds in states where there's more of a preference for katabatic forcing. And the representation of orography and temperature profiles, which I haven't really had time to go into, are probably playing quite an important role here. So I will leave it there and welcome any questions during the discussion session, and also point you towards this, this article which we've just submitted. Thank you.
Thank you, Thomas. You can ask questions to Thomas in the Q&A chat. And well, meanwhile, Dr. Ivana Serovecki, you can.
Okay, do you see my slides?
Yes, and it's
Okay,
in
perfect.
presentation mode, so it's okay. You
Okay,
have
great.
10 minutes.
Oh, thank you. Good morning from San Diego. So I will talk about impact of downward long wave radiative deficits on Antarctic sea ice extent predictability during the sea ice growth period. And I'm Ivana Serovecki, and the work was done with Ray Sun, Dave Bromwich, Jerry Zhu, Matt Maslov, and Sheng-Hung Wang. So despite the obvious importance of Antarctic sea ice extent forecast, for instance, for ship traffic, as Dave already mentioned, operational ensemble prediction systems still have problems. They tend to overestimate the sea ice edge extent around Antarctica during both the freezing and the melting season. And one parameter that plays a very important role for scale of sea ice cover prediction is the accuracy of cloud representation in models, because they're strongly coupled by cloud radiative forcing. So in winter around Antarctica, shortwave radiation is 0. So in terms of radiative forcing, what matters is surface the downward long wave radiative radiation. And oops, and the deficit and the downward long wave radiation deficit appears to be a common shortcoming in atmospheric models over the Southern Ocean. And in particular, a recent comparison of ERA 5 reanalysis with the observations from McMurdo Station in Antarctica revealed a year-round deficit in downward long-wave radiation of approximately 50 watts per meter square in marine air masses due to model shortages in supercooled cloud liquid water. So the goal of our work was then to further quantify the downward long-wave radiation biases in modern atmospheric reanalysis by comparing them with the high-latitude Southern Ocean observations from a location where marine air masses are dominant. And then after that, guided by these results, we analyzed the sea ice extent predictability, considering a case study from May 2018. We first consider ECMWF forecast, which was shown to have a very high scale. And then in order to get a better insight in the biases shown by ECMWF forecast, we use a regional Southern Ocean atmosphere ocean sea ice model and perform a number of sensitivity studies of the sea ice evolution to explore potential sources of biases of sea ice forecast, including the downward long wave radiation deficit. So observations first. This is comparison with the observations. The observations come from this location indicated by the yellow circle. This is the southernmost ever deployed flux mooring in the Southeast Pacific. So this is Antarctic Peninsula. So this is the high latitudes. And what I'm showing in the figure is the monthly mean downward long wave radiation. And the observations from the mooring are shown as black line, whereas the dashed lines show the monthly mean radiation from various reanalyses. The black dashed line shows ERA 5. The other dashed line, very similar to it, is ERA interim, and the third one is ANSEP reanalysis. So what we can see here, the dominant feature is that all these reanalyses underestimate downward long wave radiation compared to the mooring observations, and they underestimate them year round. And if we look at ERA 5, then typically the bias is between 30 and 50 watts per meter square. So Next, we look at the scale of sea ice forecast from ECMWF and consider May 2018 case study. So the left panel shows the ECMWF ensemble mean forecast on the day the forecast was initialized on 10th of May. The color shows mean sea level pressure. The black line is the sea ice edge defined by 15% concentration. And we assess the accuracy of the forecast on the day the forecast was initialized. We compare the sea ice edge with the one from NSIDC observations, which is here shown as a red line. And we see that on the day the forecast was initialized, they agree quite well, except in the eastern Weddell Sea, where the forecast sea ice extends further equatorward. The right panel, we see that the same thing, in the right panel, that these are the same two curves. The colors show mean sea level pressure bias, which we assess by comparison with ERA 5 reanalysis. And we see when the forecast was initialized, the two agree quite well. However, the story is very different 1 week later. So now this is 1 week forecast. The right panel shows the color again show mean sea level pressure bias, difference ERA 5 minus ECMWF. And what we can see is that the forecast completely misrepresents the pattern of mean sea level pressure. And if we look at these two curves that show the sea ice extent, we see that the mismatch that was present on the day the forecast was initialized now is much bigger because the sea ice in the forecast grew too fast. So the question that we now ask is what causes the sea ice to grow too fast during the freezing season? We continue examining May 2018 case study, but now using a regional Southern Ocean atmosphere ocean sea ice model that we run both coupled and uncoupled setup. In uncoupled setup, we use ERA 5 atmospheric forcing, and basically motivated by our observational results, we ask, will an artificial increase in ERA 5 downward long wave radiation reduce the overestimation of the forecasted sea ice growth that we just saw in this example looking at ECMWF forecast? So here I'm showing you the time series that starts on May 10th when forecast was initialized. And the various curves, they show the circumpolar sea ice area. The first 4 lines show the results of our hindcast model simulation. The green run is uncoupled run, and the cyan squares are coupled run. So we assess the scale of the simulation by comparison with the observations. The observations are shown with these red dots. So and we also, for the comparison, show the forecast for some commonly used operational systems. Again, here ECMWF and some other systems. So 10th of May, when the forecast was initialized, if we first focus on the results from our model simulations, then the dominant feature is that the sea ice grows too fast. So we can see that sea ice area grows much faster than in the observations shown by the red dots. And if we compare the scale of our coupled and uncoupled model simulation, for instance, with this typically used forecast shown by these various lines, for instance, ECMWF, then we see that the bias that our model was showing is comparable to the bias shown by ECMWF. So here, shown by this blue line. So then, motivated by our observational comparison, we just artificially added 25 watts per square meter to our uncoupled run, which was forced by ERA 5 forcing. And the result is shown by gray dashed line. And so if you compare now the results we were just looking at, where we used just era 5 forcing, which was the green line. Now we added 25 watts per meter square downward long wave radiation, which is this gray line. We can see that the model still overestimates sea ice growth compared to the observations, the red dots, but it agrees, it goes in the right direction. It agrees better with the observations. So then in the next run, we added 50 watts per meter square, which is along the lines of what we saw. That was the bias that we determined from the Southern Ocean flux mooring. And then we can see, if you look at this magenta dashed line, that slowed down sea ice growth, and it brought the sea ice area closer to the observations.
2
and
minutes.
Thank you. And you know, the green line looks too good to be true, which is exactly the case. This is the result from operational model that has large biases, but of the opposite sign. So they tend to cancel each other. So then we said, okay, well, you know, if we fix the atmosphere, we can slow down the sea ice growth. Now, can we slow down the sea ice growth by varying the representation of some most relevant sea ice and oceanic processes, like vertical diffusion coefficient in the ocean model, lead closing parameter in the sea ice model? We considered various definitions of sea ice edge, turned off sea ice dynamics, and in all cases, the sea ice growth was faster than in the observations. So thus, our conclusion was that in the high latitude Southern Ocean, close to the sea ice edge, era 5 may underestimate downward long wave radiation by up to 50 watts per meter square during the sea ice growth period, which is likely due to model shortages in supercooled cloud liquid water. So that's all for me. Stop share.
Thank you. You can make questions to Ivana in the Q&A chat, and she will be answering, and there will be some time at the end to discussions. And there is a, okay. My presentations, you are 21. Yes, in the last presentation, you have the last presentation, Virendra. Okay, so Dr. Payne, would you please share your screen?
Hello. Yes.
Hello.
I will share my screen here. Share screen. There we go. Can you see anything? Let me start from beginning there.
Still not in presentation mode, but yes, now you can
Perfect.
start.
All
You
right.
have 10 minutes.
Okay. Hello, everybody. My name is Robert Payne. I'm an undergraduate student at the University of Victoria, and my talk is called Substantial Seasonal Forecasting Skill of Antarctic Sea Ice in a Dynamical Forecasting System. So the dynamical forecasting system being considered in this study is the Canadian Seasonal to Interannual Prediction System version 2, or CANSIPS v2 for short. And this consists of two models, CANSIUM-4i and GEM-NEMO. Now, CANSIUM-4i is the 4th generation Canadian coupled model with sea ice modeled as a cavitating fluid, and it is initialized via an assimilation run for each ensemble, where sea ice concentration, or SIC, is nudged towards an assimilation of various data sets, and sea ice thickness, or SIT, is nudged towards a climatological mean in the Antarctic. Now, GEM-NEMO, on the other hand, has sea ice modeled with the Community of Ice Code Los Alamos sea ice model, and is initialized via the products of assimilation runs for each ensemble, where sea ice concentration and thickness are nudged towards HAD2CIS observational data and the ORAC-5 reanalysis from 1980 to 2010, and sea ice concentration and thickness are nudged towards the CCMET GEOPS analysis from 2011 onwards. Now, the objectives of our study here were to assess the skill of CANSIPS v2 in predictions of Antarctic sea ice extent on seasonal timescales. Now, I want to specify seasonal timescales there. What I mean by that is on the order of 1 month to a year in advance. So we're not thinking decades in advance nor days to weeks. Now, particular things we're going to be looking for in the results were differences between CANSIM4 and GEM-NEMO, regional variation in predictability, and the importance of long-term trends. Now, moving on to our results here. First I'm going to make a couple of quick definitions here. So I'm going to define the target month as the month for which we are interested in predicting sea ice for, or sea ice extent to be precise. I'm going to define the initialization month as the month in which we are starting the model. And then the lead time is simply going to be the difference between the two, or how many months in advance the prediction is being made in. Now moving on to the results, I'm going to quickly explain how to read these plots that you see on the right here. So if you look at the bottom two plots here, the horizontal axis is the target month. Once again, the month we're interested in predicting how much sea ice extent. And then the vertical axes are lead time, or lead. And once again, that's the difference or between the initialization and target month, or how many months in advance we're predicting for. The color is representative of the model skill. To be precise, it's the anomaly correlation coefficient, which is simply the correlation between the observed time series and the model time series. It takes on values between -1 and +1. The dots tell us that the result is significant at the 95% level based on a bootstrapping methodology. And the triangles tell us the same thing, except that the skill also exceeds that of an anomaly persistence forecast. Now, the plots on the left here, you can see the top row is for the Arctic. The bottom row is for the Antarctic. The left column is just the time series as they are, whereas on the right, the skill is computed after detrending the time series. Now, what I want to point out here is that in the Antarctic, detrending the time series did not have a significant impact on the skill here, especially relative to the Arctic, where the trend is a large source of skill. Now, this is sort of to be expected for the Antarctic, given that the trend is a lot weaker. Now, in the Arctic, I'm sure you're all aware that sea ice extent is decreasing relatively rapidly. But in the Pan-Antarctic, it was, I believe, it was increasing relatively slowly, at least until recently, the past couple of years. Regardless, you can see that the trend is not a significant source of skill for the models here. And then you can also see, if we look at the rightmost plots here, that the Pan-Antarctic shows significantly more skill than the Arctic. Next, there was observed to be a large difference in skill between CANSIM4 and GEM-NEMO. Once again, those are the two constituent models for CANSIPS v2. And then we also saw substantial variability in between different regions of the Antarctic. So you can see here in this top figure, I've plotted a simple sketch of the Antarctic here, which I've divided into 5 sectors. Now, the rightmost skill plot here, the rightmost grid, corresponds to CANSIPS v2 skill in the Ross seas, or the Ross sector rather, whereas the left corresponds to the Amundsen and Bellingshausen seas. And you can see that despite these two sectors neighboring each other, they show quite different skill. In fact, the Amundsen and Bellingshausen region was observed to show the lowest skill, and the Ross region was observed to be of highest skill on average. Now, one question that jumps out at me is why is there such a difference between the CANSIM4 and GEM-NEMO predictions? And so to investigate this, I'm showing these bias plots here. So the horizontal axes show the month. The vertical axis measures the climatological mean sea ice extent. And so the left plot is for Cancian-4, right plot for GEM-NEMO, and this is for the Pan-Antarctic. The thick black line shows the climatological mean had-to CIS observation sea ice extent for each month. The colored lines that are purple to neon correspond to model predictions for various lead times. And then the dashed red line represents the model predictions for a freely running model, so without initialization or nudging. And you can see that as lead time increases here for longer leads, the Cancian-4 tends to drift away from observations, whereas GEM-NEMO does not experience such a drift here. And you can see it sort of corresponds to a freely running model. So it appears that Cancian-4 for longer lead times tends to drift towards its more natural state.
2 minutes.
Thank you. All right, so I want to reiterate here some conclusions here. So CanSIPS v2, we saw that it shows substantial skill in predictions of sea ice extent in the Antarctic. We saw that Cancian-4 and GEM-NEMO both show substantially different skill profiles, with GEM-NEMO showing much higher skill on average. And we think this is due to drift from observations for longer lead times. And then we also saw that predictive skill depends on the region of the Antarctic being considered. Now, of course, we didn't answer the question of why there's a difference in between the different regions there and between the two hemispheres. That's a bit of a more difficult question to answer and sort of outside the scope of this study. It would probably be better explored through more systematic experimentation with model parameters themselves. Anyways, I thank you for listening to my presentation.
Thank you, Dr. Payne. If there's a question for him, please write it down in the Q&A chat. And meanwhile, Dr. Goswami can share his screen and present his work.
Well, good evening to you. I am Professor Dr. Goswami from New Delhi, India. I am going to talk about your correlations of sea salinity, Arctic sea, and so correlations and oscillates things. And not taking much time of yours, I will just share my PowerPoint presentation because I understand I have been given only 10 minutes. So I will try to finish in those 10 minutes. Just let me share the screen. Can you see?
We can see your browser, but not the presentation.
No, let me do again. Here, and this is. Okay. Is it visible now?
Yes, it's not in the presentation mode, but the.
Okay, so you can see my perspiration and my handsome face as well. Fine. Now, well, I am going to speak quickly. I just go to the slides which I made for the audience so that it is easy to understand and grasp the things. And I start with one of the rhyme of very 5,000 old epics Rigveda, that anything if you have to attain, you have to work very hard, and there's no alternative or shortcut to learning for that. So my topic is high resolution remote sensing studies of anso-energetic. There are three aspects of this topic: to study the anso-energetics, sea level variabilities mechanisms, sub-mesoscale dynamics, and the lastly to correlate with climate variability over Pacific transition areas and the Arctic Sea. Well, this is the Rig Veda, and let's go quickly to that. We all know that this climate change, the latest report about 2019 has stated that in the last 20 years, the temperature has risen by 1 degree Fahrenheit or so, and that is since 1900, not the last 20 years. And that's a phenomena of rising temperature known as global warming, you all know, and it has been estimated that there are 325 million people every year, they die. And the economic losses are due to this global warming and the climate change comes to be 125 billion annually. And it is anticipated that $342 billions will be there when the population reaches to 8.6 billion from now 7.5 billion by 2030 or so. Well, not to emphasize much, this climate change has given the unprecedented floods in the radiative areas, like in the Rajasthan of India recently, and also the floods at such areas where the generally flood do not take place, and droughts at such places. So point is that in some of the places, more than 42 years average rainfall normal, it has been increased. So obviously this all the rainfall, other things, and even this summer was the hottest summer when the temperatures have touched to 49 degrees Celsius in Delhi, breaking the record of almost 45 years or so, and similarly in the other part of the country. So this all created the big climate change and seeding of the global this greenhouse gases. So this is the very, erratic climate change is taking place not over India, all over the world. As a matter of fact, the wildfires are taking place, like recently in California, and also Las Vegas has started flooding, you see. So this is ample example, especially this year, which can correlate the climate change. Against the Washington University has reported that 2 degrees centigrade temperature and 4.9 degree by the end of century they are expecting. And of course, this climate changes, as you know, will give rise to melting of ice and rising sea levels. That is Arctic Sea or all this cryospheric area, which you call it, that will have the effect. And as we all know, the increased concentration of carbon dioxide is due to burning of fossil, deforestation and burning forests, deforestation of land degradation, water and air pollution, and global, the greenhouse gases, which you all know is your hydrofluorocarbons, fluorocarbons, chlorofluorocarbons, and nitrous oxide, carbon monoxide, carbon dioxide, and so forth, so on. So now I just give a small introduction of cryosphere. These are the places so cold that water gets frozen, and these are known as cryosphere. In the later, I will also let you know there is a Latin word "kios" from where this word originates, and this cryosphere covers all your Antarctica, Greenland, and Arctic regions, for which, and the polar region for which the scar is very much concerned, and the name itself says that how the polar meteorology is very important for us. So there are places. So the numerical ocean atmospheric forecast models have been tried, and these have been developed to some extent by us. And atmospheric challenges due to the weather events caused by mesoscale convective systems, global carbon cycle, ocean salinity, and marine pollution has been also studied. And also the ocean salinity and the toxin of the oceanic and the subsurface temperature, the sea surface temperatures have been correlated with these changes. So it is high time that we must develop an Arctic Ocean climate numerical prediction models, how we can forecast. You see, it's not important that something has happened and we are just giving the interpretation, but we must want to the humanity what is going to happen. And for that, you have to develop the forecasting models also. And so the seminar systematic research is needed to develop Arctic Ocean climate numerical prediction models to understand the major atmospheric challenges due to extreme weather events caused due to mesoscale convective systems. global carbon cycle, ocean salinity, marine pollution. You know, the marine pollution will end the marine life, extinguishing of the marine life and the biodiversity as well. So toxin gases and global warming mentioned, and over the cryosphere air, that is cryosphere area, we already talked about Arctic, ocean, subsurface ocean, and atmosphere. These are known as the cryosphere area, and already we had talked about what are the areas is well known, and especially people attending SCAR, they had been these places also, if not all, if some of the places, you see. And everybody in Europe and places and in our country, we are used to see the glaciers, and we have the highest glacier of the world, Spatial, where we had been there. I personally, we have landed when I was wing commander in Indian Air Force. And we have studied the weather over that area, you see, very strong winds and the frost and whatnot. Now, the other objectives are the kinematic and thermodynamic characteristics, lifetime distribution, trajectory, size, and three-dimensional structure. We have to study of these mesoscale convective systems, and then we have to correlate this climate variability INSO forecasting models. Means what is the relation of INSO? Taking into account the INSO, we have to develop the correlation, rigorous equations we have developed to some extent in some cases over the tropical Pacific Ocean areas. And also efforts are on to co-evaluate climate and the maritime life in the Arctic Sea. This work is going on, we have not completed yet. And the correlation of ocean atmospheric interaction with climate variability, multiple stressors, ocean as a risk of abrupt state shift, rising of sea level, melting of the glacier vis-a-vis climate variability. These are the causes which change the climate, you see, and we have to find the correlation of this with the other global weather phenomenon like ENSO. And after that, I have to next, I will tell you in the methodology, we have found out some of the optimum value which will be fed into the numerical drills model by taking into 1 degree and 1 degree grid. Anyhow, also studies are focused to explore multiple stresses on the ocean sea level variability mechanism, some mesoscale dynamics, cryospheric ice sheet stability, ice and bedrock coring, and ice sheet processes. That is, their oceanic processes, physical processes, chemical processes, by the comprehensive studies of ocean systems, interaction, risk, instability, and synergy. That is OSIRIS. So in the future, I will only talk about OSIRIS, not the complete extension or expansion of the abbreviation. So next,
2 minutes.
Physiochemical special method also we are trying to find out, and then mesoscale convective system or cryosphere region, ocean region would be correlated with the ocean atmospheric variability, that is OSIS region, and the sea surface temperature also will be taken into account. Have been taken into account some of the areas, as I told you, the Arctic Ocean we have not touched yet. A few optimal value of OSIS would be captured, developed this model, forecasting model within 1 degree grid box through the process of initialization, computation, parameterization, and by computer algorithm. Well, that's a very big topic to explain, so I will not go through the details of the methodology of the numerical modeling here, as that most of the people and the scientists know nowadays. The present investigation also aims to understand air-sea exchange during extreme atmospheric forcing to correlate air-sea CO2 exchange with climate variability. Also, we are going to study the sea level rise of greenhouse gases due to that, and control of chemical process. You see, it's very nice that we say the global warming can be controlled by plantation, no doubt. But my question is, when I was giving lecture in 2000 in NASA, is that can we wait 10 years to grow the plant and control the global warming? Answer is no. So we have to develop some of the chemical processes by which we can control the global warming vis-a-vis climate variability. Now, this background, as we these is I have shown you the transitional areas are the strong gradients areas and are the potential oceanic region of early detection of climate variability, and also western boundary currents, that is also ocean carbon hotspot. So these are the areas has also taken into consideration. And in 2000, Canadian scientists has found that the ocean atmosphere causes interaction is more evident in North Pole over the Arctic region than that of the South Pole. Well, just I want to just quote here, today's 1st August, the IMBR has given some of the projects for the climate change and the oceanic variability and all what we have talked just now. So this is a July 2022 report appeared today only. I being a member of the society, so I got that newsletter, and from there I'm just telling only those which are related with the SCAR activity. There is a collaborative research of education project in Southern Asia for sustainable use of marine ecosystem. So this the main aim is marine diversity, marine pollution, physical oceanography and modeling, and social ecological system. The other project they have taken physico-chemical cycling of nutrients and carbon in marine transitional zones, that is the transition areas, and I don't know why they have left WBCs, but this is also worth studying. So very good name, nuts and bolts they have given, and the details one can go through. And similarly, Professor Kark has attributed the glacier retreat of this Thavet glaciers was not only due to carbon dioxide and greenhouse gases, but some of the other forces were also acting. And naturally, the glacier starts melting, the sea level will rise, and marine life get destroyed, and pollution will also take place. And the end result, what report we have seen. So
please wrap it up to your conclusions.
Okay, so this is the research methodology. What we have tutored, I have told the models, we have taken this kinetic features of mesoconvective systems over Arctic Ocean regions. And further, we have also taken this interaction of climate variability with the intent to control the pollution and the impacts of multiple states over the Arctic Ocean has been studies, and convective behavior of Mesoscale system has been studies. And then research further, we have worked on satellite imageries of high resolution over the Arctic Ocean region, oceanic regions, Pacific comprising transition areas, and WBCs, that is Western Boundary Currents. And 3 to 6 hour sounding was taken. Time series was also plotted. Then your regression coefficient was calculated, and regression analysis was done by taking the Minitab app. And then the procedure steps which we suggest or we have followed for the numerical modeling is the improvement of vortex sensation, improvement of cryosphere ocean atmospheric physics, increase change vertical resolution, nested domain size, replace AOCPM with AOC NPM system, three-way atmosphere ocean wave coupling, and basic scale conformation. This is the algorithm has been followed to develop this. And the last is we also trying to develop to study the teleconnection of Arctic and Antarctic regions and their physical and diurnal processes coupled with the climate systems. This I have used while working in the Space Science Engineering Center, the DMSP pictures of USS-4, and we calculated the Mesoscale system. And following this 1 degree, we have developed this numerical ocean atmospheric climate forecast models. Thank you very much. And though it's very short, but a lot of work has gone into.
Thank you, Dr. Goswami. You can make questions to Dr. Goswami in the Q&A chat, and we will have some time to discuss the preceding papers, and we will have an open discussion afterwards.
Ma'am, I have got one request to you that when the question answer session starts, kindly give me the first chance. The reason is I am having spinal stenosis, so I can't sit longer, you see. That's my problem, medical.
Okay, okay. So please make the questions to Dr. Goswami first, please. So everything was very clear.
Oh, very
No
people are quite happy with my humble discussion and presentation, very kind of to the audience and to you as well.
Thank you very much for your contribution.
Thanks a lot. Thanks a lot. I will just sit 10 minutes more and then please, my apologies due to my health. It's
Don't
10
worry, don't
p.m.
worry.
in India. It's 10:20 p.m. in India at that point. It's sleeping time.
Yeah, yeah.
Okay. Thank you.
So we can have the open discussion since there are no questions for the any of the papers.
Okay, so I once again I take leave with all my obligation. Thanks to SCAR and all the complete audience and the organization for having given me this privilege to be with this August audience. Thank you very much. Good night to all of you, and stay
Good night.
blessed
Thank you very much.
with your cheerful families.
Thank you.
So I'd like to ask a couple of questions. Let's see now. Robert Payne, are you still online? Hopefully you are.
I am, yep.
Yes, I didn't quite catch the difference between your two forecasting systems. One which showed the free forecasts basically greatly over predicting the Antarctic sea ice extent, and the other one actually underestimating by a slight amount. So can you maybe explain for me, maybe I didn't follow all, what is the essential difference between those two systems, please?
So yes, the two models were CanCM4 and GEM-NEMO, with CanCM4 showing the drastic overestimation. So I'd say there's a large difference in their initialization procedures, which historically the initialization has been a very important factor in the effectiveness of these models. For CanCM4, which is the system that showed the drastic overestimation of sea ice extent, sea ice concentration was nudged towards an assimilation run of various data sets, and sea ice thickness was nudged towards a climatological mean in the Antarctic. And I believe this is due to a lack of available data at the time. GEM-NEMO, on the other hand, both sea ice concentration and sea ice thickness are nudged towards the ORAP-5 reanalysis, and that's from 1980 to 2010. And from 2011 onwards, sea ice concentration and sea ice thickness are nudged towards the CCMEP GEOPS analysis. And then, of course, the two.
So what that means that one is a forecast and one isn't. Is that what that means?
I'm not quite sure I understand what you're getting at there. Sorry.
Well, the one that overestimated was, I understood it to be a free forecast. You know, where you start off with the initial conditions and then you let the model run. Whereas with the second one, which involved NEMO, sounds like it's continuously nudged towards analyses, you know, like a reanalysis, for example. Is that true?
No, I don't believe that's the case. I believe GEM-NEMO is still, you initialize it for some certain date and month. And then after that initialization, you're not nudging it anymore. You let it run. And in this case, it was up to 12 months in advance, or 11 months, 1 year, essentially. But the initializations given that we are only running the predictions up to 12 months in advance, you could start the model in, say, 1980, or you could start it in 2010, and then so if you were to start the model in, say, 1980, you'd use the ORAP5 reanalysis in the initialization procedure. Whereas if we started the model in, say, 2012, and then that would be when sea ice concentration and sea ice thickness were nudged towards the CCMAP GEOPS analysis in the initialization procedure. If that
So
makes
the
sense.
point that I'm trying to get at here is, why are the forecasts so different from each other? So what is the key aspect of the initialization that gives such drastically different results?
That is a good question, and I'm afraid I don't have a very good answer for you. The best I can give you is that CanCM4 seems to experience this initialization shock quite heavily, quite drastically, and whereas GEM-NEMO, I suppose, natural state is closer to observations. But I'm afraid I can't. I don't have any concrete answers to that question. It's still something I'm looking into at the moment.
I see.
I apologize. Yeah.
No, that's fine. Okay. All right. So the second question I had was for Ivana Chirovecki, which.
I'm back.
Hey, Ivana.
Hi, Dave.
So one thing that you didn't cover was when you started the regional model prediction earlier. I think you showed the results from May 10, but there was some earlier runs as well.
Yes, that's correct. So we started our forecast from May 10th, but then also we started it maybe 3 weeks earlier and a month earlier. And when we started the forecast earlier, then the mismatch between our model hindcast and the observations was smaller than when we started it later on May 10th. The reason being is that ocean integrates atmospheric forcing. So during the prolonged time period with this adjusted downward long wave radiation forcing, the mismatch between the model and the observations was smaller.
It was
yeah.
So it's basically zero actually if you started early enough, right?
If you started the model early enough and added 50 watts per meter square, then it was zero. Yes.
Thank you.
Yeah, thank you for asking that, Dave.
David, you have a question in the Q&A? You have a fun.
Okay. Well, that's a good question. All right, so the first one asks about atmospheric forcings for a high resolution coastal ocean model. What atmospheric data set would be best to resolve katabatic winds? I think resolution is very important there. Actually, I would, the reanalyses, the finest resolution available is equivalent to about 30 kilometers, which is era 5. So actually, it depends on what your application is. If you're looking for the long term for an ocean model, then it might be better to use the reanalyses, but they don't do a great job on the katabatic winds. Shorter term applications where you're not so concerned about long-term trends, I would actually use the model forecast for AMPS the Antarctic Mesoscale prediction system, which has a much finer resolution of the order of 8 kilometers all around Antarctica. So better resolves the narrow regions of intense katabatic winds, for example. Okay, so that's the first question. Second question from Claire. Improved forecasts then showed that the reanalyses underestimate the variability of the easterlies. Okay. So can we learn from these experiments how we can improve the reanalysis product? Yes, I think so. We need better observations, for one thing, that would go into the reanalyses. And then we need the actual, because the reanalyses are a mix of short-term model forecasts and the assimilation. We need better physics into the reanalyses, and that's also part of these SOPs and TOPs. So, thank you for the question, Claire.
I could maybe jump in there.
Yes, please.
Yeah, no, that's a great point. I think on the subject of the catabatics from the earlier question, I would just add that I think if you did end up deciding to use the reanalysis data sets for whatever reason, perhaps, yeah, let's say to look at the long term, there's certainly evidence from the analysis that we've done that the MERIT-2 and JRA55 data sets struggle a little bit with the near surface temperature profile, as well as the representation. I mean, to an extent, you wouldn't necessarily expect this from the reanalysis, but the representation of the near surface inversions, which are important for the catabatics, but all three of them share this behavior, that the range of wind speeds associated with the kinds of conditions where you would expect catabatics to be dominant are not well captured. And in our analysis, we look at SOM data, so there is a kind of vertical element to it as well, but we have to exclude the lowest 100 meters of that SOM data because you need to allow time for the sonde to reach a kind of equilibrium, or the sort of background flow velocity. And so it may be that, well, given that the surface observations of wind speed are not, to my knowledge, assimilated into the reanalyses, that the wind speed observations that we have are perhaps not very well suited to constraining the reanalyses representation of those very shallow catabatics. I'm sure they play a part, and that's just speculation. But I guess I was just thinking about the presentation that we saw earlier from the astronomical perspective, and how useful those kind of vast observations with multiple levels in the lowest, certainly in the lowest 100 meters, be very, very useful.
Okay. So let's see, is there more questions? Okay.
Could I ask one question, David?
Sure.
Based on your talk, so thanks. Yeah, really interesting. Are there any plans, or is there any availability already of kind of unassimilated or sonde data which has not been submitted to GTS and therefore might be independent to an extent from the reanalyses, and allow for an easier comparison or evaluation of the reanalyses with I know that's not kind of the way that the data denial experiments are set up, but is there a way that we could evaluate the reanalyses with more kind of unassimilated observations?
Yes, there is. You're at British Antarctic Survey, is that right?
Yeah.
Okay. your colleague, Steve Colwell, has an archive of all the radiosondes that were collected during the summer spatial observing period. Many of those went out on the GTS. Not all of them went out on the GTS. I believe Steve probably knows which of those.
Okay.
All right.
That would be the crucial information. So
Yeah,
that would be really useful.
But that is a problem, getting independent information from the reanalyses, and they want to assimilate everything that's available. So there isn't much independent observations.
Right. Thanks.
Sure.
I would like to remind you all that there is an e-poster session that you can visit also. So don't forget to visit the poster sessions, because there are very interesting works in that format, you know.
Well, it looks like we've reached the end of our discussion, doesn't it, Adriana?
Yes, it seems so. Yeah.
We had a smaller number of papers in this particular session, so we had more time for discussion. Clearly, the presentations were very compelling, and there wasn't much in the way of uncertainty left as a result. So probably we can remind everybody tomorrow we have another session starting at 1100 UTC for a couple of hours. So that'll be our third session on polar meteorology, short-term climate variability. And unless I don't see any discussion or questions. So thank you for chairing this session, Adriana. And hopefully we'll see everybody tomorrow at 11 a.m. UTC. Thank you for your participation. Bye-bye.
Bye-bye, everybody.
See you tomorrow.
Bye-bye. Thank you very much.
Okay.